Welcome to this introduction to the SigLib DSP library. My name is John Edwards. I'm a director of Numerix and I'm also the architect for the library. If you have any questions about this presentation, then I would be more than happy to answer them, and my email address is shown on the slide. This is a tutorial that will provide an introduction to the library, as well as more detailed installation instructions and also how to use the library in your application. Numerix have been supplying DSP and algorithm libraries since 1991. We're specialists in telecommunications, frequency domain analysis, and other application areas of digital signal processing. We provide training and consultancy support services for our software, and we can also provide subcontract software development to help you get your project to market as quickly as possible. Over the last few years, there has been a big trend towards portability, allowing engineers to move their applications from one device to another. And so we're also able to help you with this. And the SigLib DSP library is a key capability that will allow us and you to port your algorithms between devices. The SigLib DSP library has been used in many different application areas over the years, including telecommunications and the more traditional sonar, radar, and defense applications. In the last 5 years, we've seen a big increase in the use of the library in mobile radio applications and also in voice over IP based applications. These are exciting areas where the library has been used and allows engineers to develop their applications quickly. More recently, we have also seen the library start to be used in medical and bioinformatics application areas. These are very exciting areas of research where portability between different operating systems such as Windows, Linux, and Solaris, etc. mean that the SigLib library has great benefits. The library is also written in C, which makes it much more efficient for these newer application areas than some of the more traditional script-based languages. Before we start to look at the SigLib library in detail, let us just take a look at some of the environments within which the SigLib library can be used. I'll start in the top right-hand corner of this diagram. SigLib has been compiled and used under many different real-time and non-real-time operating systems. I've already mentioned a few of the non-real-time operating systems such as Windows, Linux, Solaris, etc. But many of the modern real-time operating systems or kernels are also compatible with the SigLib library. A good example is the DSP BIOS from Texas Instruments. SigLib can also be integrated with MATLAB, LabVIEW, V from Agilent, and other integrated development environments. It can also work with tools such as Excel and can read and write both text and binary file formats. One of the many problems with developing applications today is that there are so many different environments on which different people need to run different applications. There are now cross-platform development libraries such as Port Audio and WX-Widgets, which allow applications to be written in one environment and executed on many of the other supported environments. SigLib has been used in many applications with both Port Audio and WX-Widgets. SigLib supports many programming languages: C, C++, C#, Java, Visual Basic, Pascal, Perl are just some of the many languages that can be used with the SigLib library. SigLib can run on many different platforms, including microprocessors, microcontrollers, and digital signal processing devices, and we'll see some of these listed on the next slide. This slide provides a brief list of all of the architectures supported by the SigLib DSP library. It includes general-purpose microprocessors such as x86, Pentium. It includes all of the major programming languages and scripting languages, DSPs from all of the major suppliers, StarCore, Texas Instruments, LSI Logic, Analog Devices, and many more, and also, of course, all of the major operating systems for both real-time and non-real-time systems. One question that DSP design engineers very often ask is, why use a high-level language for development? DSP is, by its very nature, a very high-performance application, so why would you use a high-level language? Over the last 5 or 6 years, C compilers have developed enormously in the field of DSP, and now most of the C compilers that are available from the DSP manufacturers and even the microprocessor manufacturers are now able to compile DSP algorithms as efficiently as anyone can code them in assembly code. So if it's much easier to port algorithms from one processor to another by using C or C++ code, we should really try and use that portability to save time and project costs. In addition to the time required to develop the application, we also need to consider the time required to debug it. And I think we'll all agree that debugging code at a higher level language is often very much easier than debugging hand-optimized assembly code. Having said that, many C and C++ compilers nowadays can compile code as efficiently as we can write it in hand. I do have to agree that there are many applications and many algorithms that can't be written as efficiently in C as they can in assembly code. The fast Fourier transform is a very good example. Try as I might over the years, I've not managed to match the performance of my hand-optimized assembly code with anything I can do in C. However, many of the DSP manufacturers and processor manufacturers provide low-level functions such as the fast Fourier transforms, and these can be linked in very easily with the SigLib DSP library. So you have the benefits of both worlds. You have the hundreds of functions that are included within the library, but you can also call on the hand-optimized library functions should you need them. Many DSP engineers nowadays are starting to work at the block or the flow diagram level. These tools make it very, very efficient to develop our applications, and many of them can call shared object or dynamically linked libraries. So if you're developing at the block diagram level and you want to improve the speed of your code running on your workstation, link in the signal processing libraries using a shared or dynamic link library, and then when you come to run your code in real time or on your embedded hardware, you can just relink with the same library, with the same API and the same function calls, but just running the code on your target hardware. We will now move on to look at the main features of SigLib in more detail. SigLib is written in ANSI C for maximum portability, but it is also written in a way that optimizes the performance of the code. So it uses lookup tables, optimum code layout and design, and other features that make the performance as good as possible. Due to its nature, SigLib is easily integrated with other languages and data processing applications across a wide range of different operating systems, as we have already seen. The library contains over 450 base functions in all areas that we've discussed already: telecommunications, spectrum analysis, and more. The code base includes more than 20,000 lines of code, and this is fully supported with example programs, and there are examples for all of the functions included within the library. Because of the nature of the library, it drastically reduces the time to market for the development of a DSP product, because you can take your code base, develop it on a workstation, and then recompile it directly for your intended target machine. The full source code of the library is available should you wish to have it. It's fully documented, and because of the portable nature of the library, it guarantees that the application code will never become redundant. The library is split into a number of different modules. The main modules are listed on the slide as shown here. There are modules for digital communications, for modulation, demodulation, channel equalization, echo cancellation, error detection and correction, timing, synchronization, and more. There are spectrum analysis and windowing functions, fast Fourier transforms, etc. Filtering, design and implementation functions for both FIR and IIR filters with fixed and adaptive coefficients. There are functions for convolution, correlation and covariance, regression analysis, image coding and processing, digital audio effects, vector processing, signal generation, control algorithms, matrix algebra, and many statistical analysis functions. The SigLib API includes functions for processing data in both a single sample-oriented process or an array-oriented process. The sample-oriented functions begin with the string SDS, all in capital letters. This indicates it is a SigLib function and that it is processing data on a per-sample basis. Equally, the array-oriented functions are indicated by the string SDA as the prefix for your function name. So the examples shown here are SDS_FIR and SDA_FIR for an FIR filter. Please note that the array-oriented and the sample-oriented functions all operate equally across array and sample boundaries, so there are no discontinuities between calling functions. In order to use many of the functions, you also need to initialize them first, and the initialization functions are prefixed by the SIF string before the function name. In the case of an FIR filter, we need to initialize the state array of the filter. Many functions do not require initialization. For example, the SDS_add and the SDA_add functions, which just add data values together, do not require initialization of internal data arrays or variables. The complete list of function prefixes are shown on the slide. I've already discussed SDA and SDS, but SigLib also has SCV for a SigLib complex vector-oriented operation, SMX for a SigLib matrix-oriented operation, SIM for image processing functions, SUF for utility functions. A good example would be the function that returns the version number for the SigLib library. SIF, I've already discussed, is the initialization functions. And finally, we have SRF, which is the reset functions. An example of the differences between the initialization and reset function operation would be in modulation and demodulation applications. At the start of your application, you will need to initialize the functions to set up the lookup tables, intermediate state arrays, and so on. But should you need to reset the data stream during operation, it is not necessary to reset the carrier lookup table, for example, only to reset the contents of the state array. So this is why we have both initialization and reset functions for some of the SigLib modules. All of the functions within the SigLib library are reentrant and multi-thread safe. This means that you can process multiple channels of data with all of the functions. While the functions maintain state information across function calls, the functions themselves do not contain any state information. All of the state information must be managed at the application level. So if, for example, you have an application that is processing 4 data streams in parallel, then you will need to maintain 4 copies of all of the state information within your program. This approach maximizes the flexibility of the library whilst minimizing the runtime overhead for managing the data. It does add an additional workload to the engineer who is writing the application, but the benefits far outweigh the cost implications. So all internal and temporary initialization data must be managed at the user application level. One thing to bear in mind when you are developing your SigLib application is that you must manage your data memory correctly in order to avoid memory overflow problems. So you should ensure that you have enough stack or heap space depending on where you allocate your data. This approach also ensures the robustness of your application, in that you as the developer can control and manage the memory allocation process to best meet the performance requirements of your system. One of the biggest problems to writing code that should be portable across multiple different processors and compilers is how to manage the different data types. Different compilers and different processors generally support different word lengths. SigLib incorporates different processors and different compilers through an include file called SigLib_p.h. SigLib_p.h specifies the characteristics of the compiler and the processor combination that you are using. You don't actually need to include SigLib_p.h in your source code because it's actually included from SigLib.h, which, as you know, is the main SigLib header file. So let us look at the different data types that are declared within SigLib_p.h. All of the SigLib data types are prefixed by the capital letters SL. The primary SigLib data type is SLData_T. This is used for all real-time data, generally floating point, but it could be fixed point as well. For accessing arrays, SigLib includes the data type SLArrayIndex_type. So all of your array index and length variables would be declared of type SLArrayIndex_type. Some of the SigLib functions use fixed point data types, and the SigLib fixed point data type is declared SLFixData_type. Other functions use character-based variables, typically 8-bit, which is used most commonly in modulator and demodulator functions. And these variables are declared SLchar_t. For image processing functions, the data is declared SLImageData_t. For Boolean variables, SigLib declares the type SLBool_t. This is not actually used at present, but it is declared for future use. The majority of SigLib functions do not return error codes because they are just processing the data. But for initialization functions, for example, which call standard I/O functions, the SigLib function will return the appropriate error code, which is declared of type SL_error_t. Finally, some of the functions return a status code, which is declared as type SL_status_t. If you wish to use a new combination of processor and/or compiler, you're welcome to go into the SigLib p.h file and edit the standard file to match your specific requirements. Full details of how these types are defined are included in the SigLib User's Guide. This slide shows how the SigLib data types are declared under Linux and Windows. The primary SigLib data type, SL_data_t, is declared as double. Remember, this is in SigLib p.h. Double data types use 64-bit word lengths. The SigLib fixed point data type is declared as long, i.e. it is a 32-bit word length, and the SigLib array index is also declared as long, and this is also a 32-bit word. The SigLib array index type is also declared as long, and this is also a 32-bit word. The table also shows the word lengths for the other important data types within SigLib. When changing between different compilers and different processors, the three main data types that are varied are the primary SigLib data type SL_data_t, which is usually changed to a float, which is a 32-bit word length, and the fixed point data type and array index data type are usually changed to short 16-bit word lengths. SigLib will automatically detect any of the supported processor and compiler combinations and choose the combination of data types that will give the best combination of performance and resolution. You will generally not need to change these data types or any of the supported architectures. As we discussed in the last slide, SigLib can support both scalar and vector variables. SigLib declares complex variables as C structures. There are two complex variable structures, one for rectangular numbers and one for polar numbers. The rectangular number format is declared as SL complex rect _s, and the polar format is SL complex polar _s. The members of each of these structures are shown on the slide. The rectangular format supports real and imaginary members, and the polar format supports magnitude and angle. These structures are declared in the file siglib.d.h, which is automatically included from siglib.h. Functions are included for processing data in both formats, as well as converting data between the two formats. SigLib declares a whole range of constant values for use in your application. All of the SigLib constants start with the string siglib_, and then the constant name. For example, the value of pi is defined as siglib_pi. All of the constant values are stored in the header file siglibc.h. Again, this header file is included within siglib.h, so you do not need to include it yourself. In addition to constant values, SigLib also declares a range of enumerated types. These are used as switches within the SigLib function. Enumerated types are declared in the file siglib.d.h. A good example of an enumerated type is the enumerated type that is used for selecting which windowing function you would like to use in your application. The windowing function is declared as SL_window_t and contains all of the types listed on the slide. SigLib includes windows for Hanning, Hamming, Blackman, Bartlett, Triangle, Kaiser, Blackman-Harris, Rectangle, and Flat Top window. There are many different enumerated types and constant values supplied with SigLib, so I would refer you to the SigLib User's Guide for further details on all of these. As I described in the introduction, SigLib is provided with a large number of example programs. There are examples for every one of the SigLib functions provided in the folder siglib/examples/c-examples. Within that folder, there are batch files for building the examples. The C-examples, they will actually recompile with any compiler, as long as you remove the graphics functions first. Unfortunately, this means you won't have access to the graphs, but you will be able to recompile the code without the graphics functions on any target processor, even an embedded DSP or an embedded controller. As well as the C examples, we also have examples for C#, Perl, Java, C++, both static and dynamic link libraries, Agilence V for DSPs, and for a range of other different targets. These examples are all included in the siglib/examples directory. Let us now take a look at a simple SigLib example that will calculate the fast Fourier transform of the dataset that we provide. I have split the source code up into two slides just to make it easier to read. In this slide I have the code that includes the header files, math.h and siglib.h, the constant definitions, and the global variables. In this example, we are going to generate a sine wave, and we have declared the magnitude and the frequency of the sine wave. We are then going to window the data and then perform our FFT. An interesting point to note here is that the frequency of the sine wave is normalized to 1 Hz. All SigLib frequencies are normalized to 1 Hz to ensure maximum portability across different applications. If you wish to generate a frequency with a particular sample rate, then all you need to do is scale the frequencies appropriately for your application. In the global variable declarations, you can see that we have declared pointers to our real and imaginary data, our window coefficients, our result data, and our FFT coefficients. We have also declared a global variable sine phase, which will store the phase of the sine wave that we are going to generate. This is so that we can generate sine waves that have continuous phases across array boundaries. This is a very common requirement within SigLib. When you're processing data across array boundaries, you very often need to maintain the state of that data. On the next slide, we will look at the main function. This slide includes the entire source code for the main function for performing the fast Fourier transform. It may help if you select the full screen mode for viewing this particular slide. At the top of the main function, we have 5 lines of code which declare or allocate the memory space for the data that we are going to process. You'll notice that these functions are SigLib utility functions that perform the vector array allocation. Vector arrays are just linear arrays of data stored in memory, and in actual fact, SUF_vector array allocate typically just links to the malloc function. While you can use the malloc function in C, the benefit of using the SigLib function is that it will allocate the appropriate length of the array according to the data type that you are using. Having allocated the appropriate memory arrays, we could verify that the pointers are not null pointers in exactly the same way we would do with standard C to verify that the arrays have been allocated correctly. I've not actually included that piece of code within this function because then the code would not have fitted on a single slide. Having allocated the memory, we then go on to initialize our fast Fourier transform function. This particular function will return an error code if there is any problem within the function, and we check the error code having returned from the function. While most SigLib initialization functions return an error code, the SigLib data processing functions generally do not. This is because the SigLib data processing functions typically just perform standard multiply and add mathematical operations, and there is no error code to return. This function initializes the FFT coefficient array, and hence we have to provide the appropriate size for the fast Fourier transform. You will also notice that there is a null fix data pointer included in the function parameter list. The FFT functions can actually work in several different ways, one of which uses a fast lookup table for the bit reverse reordering of the data. In this particular example, we're not actually using the fast lookup table, and so we don't need to provide a pointer to that table. Hence, we've just provided a null pointer to the function because the pointer is never used. Having initialized our fast Fourier transform, we will now initialize our window function using SIF, SigLib initialization function, _window. We have a pointer to the coefficients. We have the enumerated type, SigLib _Hanning, to select the type of window. We have another parameter 0, which is not actually used with the Hanning window type. And then we have our window length, which is the same as our FFT size. Having initialized the FFT and the window, we now need to generate our sine wave signal. This is performed with the SDA, that's an array function, signal generate. We set the phase to 0, and then we call the SDA _signal generate function. We have our destination array, which is the pointer to the real data array. We have a parameter that's specifying a sine wave, the magnitude, and the fill mode. There are various other parameters included here, including the frequency and the size of the array that we are going to fill. The signal generate function can generate many different types of signals, including sine waves, square waves, pulses, and so on. These different types of signals all require different types of parameters, and so some of the parameters are set to 0 when they're not used. A sine wave is a very simple signal, and so the only parameters that we really need to provide are the magnitude and the frequency. We can now apply the window that we initialized earlier to the data that we have just generated. And to do this, we will use the SDA SigLib data array _window function. The input data is the pointer to the real data. The output is another pointer to the same array, so this function will work in place. We have a pointer to the window coefficients, and we have the window size. Having performed the window operation on our real input data, we can now perform the fast Fourier transform. The input data sequence is a real sequence, and so we will use the real FFT function. This takes a real input data sequence, but will generate a real and an imaginary output sequence. Hence we require one pointer for the input data, P real data, but two for the output data sequences. One for the real, one for the imaginary. So the real data sequence that is used for the input will actually be overwritten by the result real data. For the FFT function, we also need to provide a pointer to the FFT coefficients. We have our same null pointer because we're not using the fast lookup table mode in this particular example. We need to provide the FFT size and also a parameter which is the log to the base 2 of the FFT size. Having performed the real FFT function, we will now scale the results because whenever you perform a discrete fast Fourier transform on a dataset, the output data is scaled by the size of the fast Fourier transform. So we need to take the output of the FFT function and scale the data back down to the appropriate size. So we use the SigLib data array function complex scalar divide, and this will scale the data by the FFT size as shown in the slide. Having scaled the output results, we then need to convert our results to dB using the log magnitude function, and this will give us our real result data in the array pointed to by P results data. Having performed all of these functions, we now have the results stored in that array, and we could plot the data on a graph, or we could use that data for some other functions. The choice of what to do with that data is entirely dependent on your particular application. But this example has shown you how to calculate the FFT. Having finished all of our processing, we now need to free our memory, and so we call the SigLib utility memory free functions, and these will clear our pointers. I have not included all of the lines for freeing up the memory in this example because I was running out of space on the page. If we were to include the GNU plot version of the Numerix host library within our example to plot the results, then we would see a graph such as the one shown on this slide. The graph shows the 512 points on the horizontal axis for our output array, which represents our frequencies from 0 Hz up to the sample frequency, and hence we have two frequency peaks mirrored around the Nyquist point at bin 256. And on the vertical axis, the power in dB for our signal. This tutorial has summarized the main features of the SigLib DSP library. If you wish to use the library and gain the maximum benefit from the library, then I would thoroughly recommend that you read the SigLib User's Guide, particularly the Quick Start section for the processor and compiler of your choice. The SigLib User's Guide is a big document. You don't need to read all of it, but it does contain a lot of useful information that you will need to know to get the most out of the library. You'll find that you only need to refer to the parts specific to your compiler or device. If you're evaluating SigLib, then you can download the complete documentation set from the URL shown in the presentation. In summary, SigLib is a very powerful library of DSP functions that is portable across a great many different processors and operating systems. The functions are very easy to use in new and exciting applications. The API provides the following benefits. There is a strict naming convention for the data, constants, and function names, which allows ease of use and portability across all of the supported architectures. There is a very simple yet powerful data structure format, and there are a large number of vector management functions for creation, deletion, and general management. This slide contains a number of URLs that you may find useful. Please feel free to click on any of the URLs and read the information that they contain. At the bottom of the slide is a link to our technical support. Please do not hesitate to email us if you have any questions. Thank you very much for watching my presentation, and please do not hesitate to contact me if I can be of any further assistance.